Okay, so I'm very excited to introduce our last speaker of this session, Matt Weiss, and he will answer the question, how quantum is QBism? The floor is yours.
Yeah, thanks to everybody for making this an amazing conference. It's been a really lovely experience. My talk is How Quantum is QBism, which sounds a little bit like a provocation, and maybe it is, but I do identify as a cubist. And really, what I'm going to try to, the cubists are paying me. So what I hope to do is show that the formalism that cubists have developed, really, like in John's terms, just for the first couple layers of his onion, apply more generally than just to quantum theory. They work, in fact, for classical probability theory, as well as GPTs more generally. And so I'll go through a little walkthrough of how that works, and especially if you're not that familiar with our formalism, this might be a good introduction. And there'll be a little bit of a twist on it in terms of the way that it's usually represented. But then, given this fact that the formalism can be used, more broadly, I'll offer some thoughts, not necessarily original to me, about how cubists can, pick out quantum theory uniquely. So Rudiger and John have set me up very well for this part here. It's just worth reminding ourselves that cubists are devotees of De Finetti. And so we work with a sort of subjectivist notion of probability. And De Finetti showed that you can get the axioms of probability theory from the demand that you be Dutch book coherent. In other words, he glossed probability as the price that you'd be willing to pay for a lottery ticket that pays out $1 if the event occurs. And, so you're going around, you're placing bets, you've made these probability assignments, and it might be, you might lose money, you might gain money, depending on whether your horse comes in, but you don't want to get yourself in a situation that, you definitely 100% guaranteed lose money. In other words, you don't want to get Dutch booked. And you can show that simple demand allows you to, derive the normal rules for working with probabilities. They have to be not negative in 0 and 1. And so this dramatizes the idea that probabilities aren't out there in the world, but are tools agents use to manage their expectations. And so, as we've all heard, QBism views quantum theory in much the same way. It's a normative guide, but in particular for agents betting in a non-classical world. And so the formalism that we've developed basically involves the central player is this notion of an informationally complete reference device. And so this allows us to substitute probability distributions over the outcomes of these reference devices for density matrices, and thus make very clear that it's perfectly okay to treat quantum states as beliefs. And non-classicality itself, usually we say something like it's reflected in the addition of new normative constraints to probability theory. And the Born rule is one such normative constraint, and it appears in the formalism as a deformation of the law of total probability. So the reference devices that are closest to the heart of the cubist are those built out of seq POVMs. And so I'll say a little bit about what they are. Symmetric informationally complete POVMs. Geometrically, you can think of them as a set of d-squared equiangular lines in a d-1 dimensional complex projective space. Quantum mechanically, they furnish a set of operators corresponding to a very nice informationally complete measurement. In other words, the POVM elements span the operator space. And so in general, we elevate them to the standard quantum reference measurement. And so for concreteness, in the case of a qubit, here's the Bloch sphere, the so-called seq states, there's, they form a regular tetrahedron inscribed in the sphere. And then the POVM elements represent the effects, representing the seq measurement, are simply rescaled. Just in case not everyone is familiar with the concept of a POVM, I thought I'd just say a little bit in a more like traditional vein about what a POVM is. Ultimately, we take POVMs or generalized measurements to be really like the fundamental kind of measurement. But the usual way of motivating it is to first talk about von Neumann measurements, which are associated with self-adjoint operators. And these measurements have the property that they're repeatable in the sense that, say, you measure Pauli X and then you do it again, you should expect to get the same answer 100% of the time. But they're not informationally complete. In other words, if you've assigned probabilities to the outcomes of a Pauli X measurement, that is not equivalent to specifying a density matrix. It's underdetermined. But the usual story is that, well, suppose you allow your system to interact with an ancilla, which could be an arbitrary dimension. Maybe there's a unitary interaction coupling them, and then you do a von Neumann measurement on the ancilla. When you rewrite it so that all of this is taking place on the original system, you're able to get your POVM elements. And so they're a set of positive semi-definite operators that sum to the identity. And the Born rule takes this form, which we've seen before. And all this is really doing is making sure that the probabilities you get over all the outcomes of a measurement sum to 1. And the important point that I want to bring up here is that precisely because the number of POVM elements is not limited like by the dimension of the Hilbert space, you can have this phenomenon of informational completeness. In other words, you could actually have a set of POVM elements that span the space of operators. And so these probabilities end up, being equivalent to the specification of a density matrix. But, unlike the von Neumann measurement, these measurements are not repeatable. In fact, for the qubit seq, suppose you prepare a seq state, and then the preparations of the 4 seq states are represented by the columns, and then suppose you do a seq measurement that's represented by the rows here, you can see that you only get the same answer half the time. And then any of the other 3 is 1/6 of the time. And that is the fact that you get a 1/6 for any of the other 3 outcomes is the symmetric part, okay? So indeed, there's the picture, of course, it was inevitable. So John's already set this up. I guess I will just emphasize a couple things. So we have our quantum system, we have a reference measurement, and I want to emphasize here, so this is going to be our reference device, and it consists of 2 parts, a measurement and then a choice of post-measurement preparations. And so, okay, using the Born rule, we can calculate these probabilities for the outcomes of the reference measurement. We can calculate the probabilities for if one of these post-measurement guys goes in here, what's the conditional probabilities? Where, notice this is written probability of dj given hi. Of course, what's going in here, we're thinking of it as sigma I. But of course, the idea is that conditional on getting the outcome, say 1, you prepare the first post-measurement state. And so you can use the outcome of the reference measurement as a proxy for the state preparation. And so then we have our probabilities for the reference, our conditional probabilities that characterize the subsequent measurement in its relationship to the reference. And then finally, we have the probabilities for going straight into this subsequent measurement. And we can consider the so-called sky path, or the hypothetical path, if you like, and the ground path. And the sky path is the probabilities for the outcomes of D are simply given by the law of total probability. But it's not hard to show that you can write these probabilities Q in this form. Normally, it would be just trace of dj times rho. But instead, you can write it in terms of, well, phi is a matrix. And we will talk about it in this. I will talk at length about this matrix, which we call the Born matrix. What's kind of cool is that for a seq-based reference device, the action of this matrix phi takes a beautifully simple form, which you have here. You simply rescale your probabilities with respect to the reference device and subtract off a little offset. And that's it. And so QBists have elevated this expression, this equation, to an expression of the world's fundamental non-classicality, calling it the Ergleichung. And there's a sense in which, according to one measure at least, this form is as close as you can get quantum mechanically to the law of total probability. In other words, the difference between these two expressions, law of total probability and the Born rule, is just the presence of this matrix phi. And there's a certain quantifiable sense in which this is the closest you can get, assuming quantum theory. Okay. And so, inspired by that sort of thing, QBists have often wondered whether it would be possible, to reconstruct quantum theory from the Ergleichung alone. And that's not going to work. How quantum is the form of the Ergleichung? Strictly speaking, there's nothing particularly quantum about it. Even in classical probability theory, in generalized probabilistic theories, Ergleichung expressions are ubiquitous. And so the question will be, how can we sharpen the QBist conviction that seeks are the royal road to quantum theory? So I'm going to begin firmly in the realm of classical probability theory and motivate the QBist formalism for working with the information complete reference devices, and show that the use of this formalism is really orthogonal to this question about hidden variables. And I hope this exercise, which I'll go into some detail about, will give everybody a better feeling for why the QBist formalism works. So suppose we have a shape measuring device. Okay, something goes in, we don't know what it is, and one of three lights blinks. It's a circle, it's a square, it's a triangle. And let's assume that something's shape depends in some way, who knows how, on its color, red, green, or blue. And so suppose I should clarify here. So in the setting that I'm imagining, let's assume that we know what color it is. I'm calling it a hidden variable, but suppose that we know what color it is. Okay, so we send things of different color into this device, and after playing around for a while, we come to some judgments about these conditional probabilities. And so now I have this matrix which encodes my expectations. So as I said, something read into the device. What's the probability that the circle light blinks, and so forth? We'll call when you see this notation, P shape given color, just imagine in your head, it's this whole matrix, just to be clear. I'm going to, in general, work with this sort of matrix notation. Okay, so I'm going to call a state a state of uncertainty about color. Here we go. And then naturally, we can use the law of total probability to transfer our expectations about color to our expectations about shape. by simply doing a matrix multiplication. And I'm going to call the rows of this matrix effects, looking ahead to when we generalize to the GPT case. And indeed, notice that we can write the probability, say, of the circle light blinking as the action of a linear functional, in other words, like a row on a column. In other words, a state. So suppose we also have a shape preparation device. We press a button, circle, square, or triangle, and it prepares something of a certain color. And after, plugging away at this device for a while, we characterize it as best we can. We come to some judgment about this matrix color given shape. And we can indeed think of the columns of this matrix as themselves states. In other words, this is the state that we'll assign given that we press the circle button. And then finally, suppose we have some third measurement which measures something face. Is it like heads or tails? And again, this in some way depends on color. And by sending many different colored things into the device, we ultimately might come to some judgments about these probabilities. Okay, so what's the catch? So far, I've assumed that we simply can just look at the color of one of these objects. And we've specified no device for measuring color itself. But what if color was not observable directly? What if it was, actually a hidden variable? Question, could we calculate the face probabilities in terms of the shape probabilities without using color as an intermediary? And, in general, that might not be possible, but sometimes it is. And so one way to do it is to introduce what I'll call a probabilistic reference device. And, it's just what we've seen before in the sky-ground picture. In other words, we have a reference measurement followed by a reference preparation device, and imagine that something comes in, and if the circle light blinks, then the circle button is pressed. So we can either take the sky path, and so I've just sort of written out, all these, chained uses of the law of total probability. In other words, we start off with something's color state, and then we get its shape state, the assignment of probabilities to the outcomes of this measurement. And then, depending on which of these buttons is pressed, something of a certain color comes out. And when we combine these two, the face given color times color given shape, we get face given shape. Okay, nothing too strange there. The question is, can we re-express the ground path without using color as an intermediary? And so this is where, the formal tool is introduced, the so-called Born matrix. And I will call a Born matrix any matrix that satisfies this identity. So this was the matrix whose columns I said I'm going to think of as states. And this is the matrix whose rows I said I'm going to think of as effects. And so a phi matrix is any matrix such that the left-hand side has to equal the identity. So why would we want that? If we simply take our expression and insert the identity, and then chain these together and chain these together, we're able to write our probabilities for the face measurement in terms of the probabilities for the shape measurement, this matrix phi, and the probabilities for the face measurement given the shape measurement. And so color has completely vanished from the story. And the only cost was deforming the law of total probability. Okay, does that make sense? Feel free to ask questions or this is really the third talk in rapid succession. So if anyone feels the need to, at any point during this talk, to stand and stretch, I won't be offended. So the phi matrix, okay, I like characterized it in this sort of abstract way. But how do you actually find it? Well, it's not so hard. If you just left multiply by p shape color and right multiply by p color shape, then when you chain p shape color to p color shape, etc., you get this expression. P shape shape phi p shape shape equals p shape shape. Okay, it's a mouthful. I like to just think of it as p phi p equals p, where p, or p shape shape, is what I'll call the self-conditional probability matrix. And it's just, if you take the preparation device and route it into the measurement, what's the probability that, say, you get a triangle given that you pressed circle or whatever. So just like to put some numbers on it to make it more concrete, suppose that p shape color was given by this matrix, p color shape was given by this matrix, multiply them together, and we get this, which I just cleverly chose because it is equiangular. And so we have a sort of a classical seek here. If you're interested, just by the by, this equation p phi p equals p is the defining equation of a type of generalized matrix inverse called a one inverse. The terminology is, completely not illuminating. Generalized matrix inverses are classified by which of somebody's list of axioms that they satisfy. And whoever made the list numbered them 1, 2, 3, 4, 5, etc. And ever since, people have been categorizing these generalized inverses by which axioms numbered in accordance with this list that they satisfy. And the first one happened to be, basically p phi p equals p. They're not hard to calculate. You can simply use like a singular value decomposition and get it. The crucial step, though, is that if we assume that the effects and the states are informationally complete, in other words, that they span the space of, probability vectors and, on the other hand, response functions, if you like, then these two expressions are equivalent. P phi p equals p, from which, we get the idea of how to calculate phi from P, the self-conditional probability matrix, thus grounding phi itself in probability judgments, to S phi E equals the identity, which is what back here we inserted into our expression in order to get rid of color. So I worked out an example. I don't know if this is like that helpful or not, but it might be useful to like just see, in sort of a step-by-step way, like how this plays out for intuition. I mean, what's nice is that in the case of a minimal informationally complete reference device, where the effects and the states form bases, phi is just simply the inverse of the self-conditional probability matrix, which I had chosen to be this. And so when we take its inverse, we find that phi, the action of phi, takes a beautifully simple form, which I've written in matrix notation. But it's really just the same as what we saw for the seek Gleichung, but with different parameters. In other words, we take the probabilities for the outcomes of the shape measurement, rescale them, and then subtract off a piece. And so here, the Gleichung appears even in this, quite obviously classical situation. And, the point is that we can come to judgments about P shape, P face given shape, P face given face, etc. And from the latter phi without like ever contemplating a color. In other words, we built up the formalism by kind of assuming the color was there, but we can completely dispense, like, in a way with that hypothesis. And why does it work? I mean, like in general, phi is going to depend on the choice of, reference states and effects, but only sometimes will it take this nice form of like an Gleichung. And basically, the key idea is that if you consider this as a measure and prepare channel, it's a depolarizing channel. So, for example, the channel operator in this case would be, okay, suppose we send something of a certain color in, there's a shape outcome, conditional on the shape outcome, we prepare a state of color, but we don't know which outcome actually occurred. That whole operation could be described by this channel operator, which you can see is depolarizing in the sense that it's a mixture of the identity and the projector onto the state of maximal ignorance. In other words, the way that the channel operator acts on one of these color states is simply to mix it with the state of maximal ignorance. In other words, 1/3, 1/3, 1/3. That's what depolarizing means. And so if we return to this expression up here, I've just sort of written so what I had before is P face given shape equals P shape with phi in the middle. I've expanded it back out and restored the references to color, just to show you that if we consider this whole expression, which by construction should give us P color, what happens if we sort of progressively like play out this equation? In other words, if we know what phi does, we simply rescale and subtract off this bit. Now let's bring P color shape in. This turns into the channel operator. This matrix, its rows sum to 1. And this is just the column vector of all ones. And so we get just the column vector of all ones back. And so we also know what the channel operator does. It gives us this. And so that gives us the vector of all 1/4. 4 comes in, subtract it off, we're back to P color. So just just the reason I went through this in somewhat laborious detail is just to emphasize that, in the case where you have a depolarizing channel, what phi is really doing is it's sort of like pulling you back in such a way that when the depolarization happens in equation terms, you get right back to where you began. Okay, so in a way, that's most of the main points that I want to make in this talk I've already hit, just in laying out that sort of simple classical example. It's really natural to generalize like all of this to not just quantum theory, but generalized probabilistic theories. I mean, the whole thing is just perfectly suited to throwing away the assumption that like there's a hidden variable. Even in the classical case, we've seen you don't even need it. So just to refresh your memory, or maybe it's an introduction to it for the first time, if you're not that familiar with like the GPT framework, I'll just remind you that, as I alluded to earlier, in classical probability theory, a probability can be seen as coming from a linear functional acting on a vector. And, that's just the same structure we find in quantum mechanics. You can think of the vector as being the density matrix and the linear functional as take the trace with this POV element. And here I've written it in this sort of soft bracket notation where I've sort of expanded everything in terms of some orthogonal operator basis. Okay, this is a somewhat heavy looking slide, but these are just the sort of the fundamental theorem of GPTs. In other words, I can view a bunch of states and effects as living in a convex subset of a vector space and its dual if some like really quite natural assumptions are satisfied. So if I have a probability function mu, in other words, it takes an effect in a state to a probability. And if this function satisfies some, as I say, rather natural assumptions, then we have this, we're licensed to embed. So in other words, so what are they? It's simply, if two states are indistinguishable by any effect, they must be the same state. Similarly, if two effects two effects are indistinguishable by any states. They must be the same effects. There's a trivial effect that always gives probability 1. I have to thank Michaela as well for having, I didn't mean to laser point you, for in some ways alluding to many of these things. There's a trivial effect that gives probability 1 on all states and an opposite effect for every effect. And basically something that lets you take convex combinations. In other words, if I have 2 states, S1 and S2, and I take a mixture of these probabilities, then there's always some state that just gives me that probability directly, and the same for effects. Okay, and so once you can do that, like everything's fine. You have a set of states, it's a convex subset of the vector space. The effects are linear functionals that are non-negative on those states. We can take convex combinations. There's a normalization functional, which I will write as soft bracket I, which I won't even specify the form of it. Michaela chose it to be the 111's vector, but you need not. The measurement is a set of effects that sums to this normalization functional, but indeed for classical probability, that is what you get for the normalization functional. And so I'll go through this rather quickly because it's just the same story. In other words, we have a set of informationally complete effects and states. We have some kind of reference device. You can always do this in any GPT, even in the minimal case where you have, just the fewest number of elements you need to span the vector space. Again, you can form this self-conditional probability matrix, your judgments about what happens when you route the output back into the input of your reference device, which, before was P-shape color times P color shape. Here, I'll just represent it as E times S, where E, the rows are effects, and S, the columns are states. Before, these were, column stochastic matrices, but, let's just throw that out. They can be, they could be whatever you like, as long as they satisfy the geometry of your GPT. And again, a Born matrix is just any matrix phi that satisfies this equation, which is equivalent, thanks to informational completeness, to the equation of a 1 inverse. And if we have another measurement A, which will be a matrix whose rows are the effects for it, then just as before, we can, the probability, again, this is a probability vector. So this is the vector of probabilities for the outcomes of A given some state rho. We can insert S phi E, and A on S is just the probability of the outcomes of A given the reference preparation. E on rho is just the probabilities for the reference measurement. And we're back where we started. And again, I emphasize, the whole point is that everything in this expression derives from an agent's probability assignments for the outcomes of actual measurements. We sort of went through the sort of song and dance about GPTs, but you can sort of forget about it at this point, because now you're just working with only objects derived from probability judgments. And so, as Rudiger was emphasizing, the Born rule then is really a consistency relationship between these probabilities. And you can even be a little bit more specific, there's certain linear algebraic constraints that these must satisfy. In other words, PE must lie in the column space of the self-conditional probability matrix, things like that, which you can just think of as, if they're not satisfied, that's just a prod for you to, maybe adjust your probability assignments, including the judgment of informational completeness. Okay. So under what conditions can we use an Ergleichung-like expression? I will generalize the Ergleichung to this more general form. We're going to rescale our probabilities, and we're going to subtract off a bit. Where now we allow that these might be different. We'll assume that there's some weights that sum to 1, and we can think of them as biases. In other words, you can think about, suppose you just suppose you just throw garbage over and over again into your reference device and just look at how often the lights blink, I think a simpler way, like a more mathematical way of looking at it, is that the biases will be the eigenvector with eigenvalue 1 of the self-conditional probability matrix. So there'll be a probability assignment that you judge is left invariant if you act on it with this matrix, which essentially implements the channel. Okay, whatever. So here's sort of the main theorem. You can always write the deformation of the law of total probability, in other words, the action of the matrix phi, in this form, if and only if the channel operator is depolarizing. If you think about how this operator acts on a state, E on the state gives you a probability, and this gives you a statistical mixture of the post-measurement states. And the depolarizing parameter A is just the same that appears there. And what's kind of cool is that given like any measurement whatsoever, you can always find a set of informationally complete reference states that yield a depolarizing channel. And so you can actually use, the generalized Ergleichung to process probabilities for any measurement, like in any GPT, classical or not, as long as you're free to choose your reference states appropriately. And there is indeed always a way to choose. I just wanted to quickly bring up like a special case. Michaela also mentioned morphophoric measurements, and I won't say too much about them, but they turn out to be a sort of a special case of this construction. So you have a measurement, and you want to pick some state so that the channel is depolarizing. It might be that you could choose them to be proportional to the reference effects. And it's always possible, in principle, to choose post-measurement states like that if you're working in a self-dual GPT. In other words, there's a duality between states and effects, which is the case for quantum theory. Density matrices and P of M elements are both positive semi-definite operators. More generally, you could consider non-self-dual GPTs where that's like not the case. But you could always depolarize your states sufficiently that they become valid. And either way, if that's possible, then that actually turns out to be equivalent to this notion of a morphophoric measurement, which has the cool property that the map from the state space into the probability simplex represented by the measurement is a similarity. In other words, it maps the state space into the simplex in such a way that distances are preserved. It might be rotated. In general, it might even be translated within the probability simplex. So a little bit about them. They always exist in any GPT. They're always informationally complete. For a morphophoric meek, where you have like the minimum number of elements necessary, the choice of post-measurement states is fixed. Now, it's an interesting fact that, forget about morphophoricity for a second, if you have an unbiased Meek reference device, in other words, where all those weights are flat, then regardless of the post-measurement states you choose, if the associated channel is depolarizing, the self-conditional matrix will be equiangular. And all that's, and a natural consequence of that is that unbiased morphophoric Meeks are just Seeks, although not necessarily extremal. And so this, what I want to do now is just show you that if we assume unbiasedness and we assume morphophoricity, or let me say it a better way. So if we assume unbiasedness, and if we're working in quantum theory over the complex numbers, if we take our reference states to be pure, then this fixes this parameter A. And you can show that the pure morphophoric quantum measurements are just, if this is meaningful to you, the complex projective 2 designs. And the minimal complex projective 2 designs are just the Seeks. And so when we substitute here n, so we took the weights to be 1 over n. If we substitute d squared for n, we recover the equation which we began with, which is the equation for a Seek reference device. Okay, so I've shown that the QBist formalism has nothing particularly quantum about it, both from the point of view of the sort of Born matrix formalism, sort of sky ground picture, but even from the point of view of the Ergleichung. It really just follows from the assumption that the channel associated with the reference device is depolarizing as well as informationally complete. So I guess what I want to turn to now is the question of what does make quantum theory special? In other words, in quantum theory, so we think, you can always find Seeks that are pure. In other words, the example that we began with when we were considering the so-called classical Seek, way back, I won't go all the way back, it could take a while. That was a Seek that lived within the probability simplex. The extremal states of the probability simplex are just the basis vectors, which is quite unlike the quantum case, where the Seek states are in fact pure, they're extremal, they live on the boundary of the state space, and they're perfectly distinguishable by some measurement. So I now want to sort of dramatize one way of thinking about what makes the Seek reference measurement special. So when we started the talk, we assumed that color just naively was inspectable. We could just see something was red, blue, green, whatever. And in doing so, we implicitly employed the ultimate classical reference device, for whom the self-conditional probability matrix is just the identity. And, while this is kind of trivial, it's worth enumerating its properties. And the slide I'm about to show you has a big list on it, which in a way is a joke because it's something which is so simple. But given everything we've learned, we can now sort of think about it in a somewhat sophisticated way. So it's a measurement that simply reads off the color, prepares something with the same color. So this post-measurement states are proportional to effects. That's kind of special. Considered as a measurement prepared channel, it's the identity. Oh, but that's a special case of a depolarizing channel. It's trivially morphophoric. Well, it just maps the probability simplex to itself. Okay, it's unbiased for sure. When A is 1, the Ergleichung, it just collapses to the law of total probability. It's a Meek. Okay, it states where its effects and states were linearly independent. It's in fact a Seek. The states are extremal. They could correspond to vertices of the probability simplex. Every state can be distinguished by some effect, and every effect can be perfectly distinguished by some state. And the states and effects perfectly distinguish each other. And so now you can compare that to the properties of a seq reference device. Again, the post-measurement states are proportional to effects. It's a depolarizing channel with this parameter for A. It's morphophoric, it's unbiased, it's a meek, it's a seq, the states are extremal, and indeed they correspond to the vertices of the simplex. And every state can be perfectly distinguished by some effect. So the only differences are the value of the depolarizing parameter, the fact that the state space is only mapped to a subset of the probability simplex, and the states and effects don't perfectly distinguish each other like as a whole. And so you could argue that the pure seq reference devices in quantum theory are like the closest analog to the trivial classical reference device. And that's not true in like just one GPT, so to speak, but in a whole infinite sequence of them, one for each Hilbert space dimension. This part, how am I doing on time? Have I totally abused my, okay, I'll skip this part. All I wanted to say is that you can consider the question of seq existence in sort of various foil theories. The sort of nuclear family of quantum theories is given by the Euclidean Jordan algebra. This is sort of the close-knit family of quantum-like theories. And they just sort of essentially consist of quantum theory over different number fields. And, there's been a lot of work done, to show that in the case of real vector space, quaternionic vector space, seqs don't seem to exist. That is to say, pure seqs don't seem to exist. There's a sort of a special case, the spin factors, in other words, the GPTs whose state spaces are higher dimensional spheres, like they do have pure seqs. You just inscribe a simplex into the sphere, but they're pretty boring because the maximum number of perfectly distinguishable states is just 2. And so that's leads to a sort of question: is it possible to define an infinite sequence of GPTs of increasing dimension, for which are not Euclidean Jordan algebras, for which pure seqs always exist, and the maximum number of perfectly distinguishable states scales with the dimension, as it does for classical probability theory. And, maybe there's some other things we could think of, but that would be yet more evidence that quantum theory over the complex numbers is like the gentlest possible modification, actually, of classical probability theory, given that nature forgoes hidden variables, or in the language of Blake Stacey, has vitality. And, as part of this project, we study these things called Q-plexes, which you can read more about. So that's pretty much all I have. Just to recap, the QBist formalism really works, not just for quantum theory, but more generally, classical probability theory, for generalized probabilistic theories. And I see that like not as a bug, but as a feature. Like it's cool. It's GPT agnostic. It's really grounded in your probability judgments, which you can make regardless of talking about state spaces or effect spaces, if you like. Even the famed Ergleichung is available for any GPT, for any measurement, but the existence of pure seqs is much more controversial. And as I say, they generalize in this very elegant way the trivial classical measurement. And thus, you could have even just sort of imagined their existence without even knowing anything about quantum theory, and hopefully will come to give us a way of nailing down why particularly quantum theory over the complex numbers over any other GPT. Thank you so much for listening.
Okay, thanks so much for your talk. Questions? John?
I mean, while the form may be achievable, those particular numbers are sacred.
Yeah, that turns out to be the case. Yeah, the numbers themselves are the sacred part. Yeah, for sure.
Okay. Are there any further questions?
You want to press some way?
No.
No. So thank you very much. It was a very interesting talk. Thanks a lot. I have a question about that word I cannot pronounce. URL. I don't know.
Oh, Ergleichung? Well, I can barely pronounce it. Yes.
Is it correct if I say that?
Ask one of the many German speakers here. Beautiful.
Thank you.
Music to my ears.
So is it correct if I say that it's a requirement on the dual frame of the POVM to be itself depolarized, but maybe depolarized the other way around, so with negative weight? So like
yeah. You can write you can write the dual elements in a very simple form where you're basically just like
that they are the polarized version of the effect of the original POVM. Is that the URL whatever?
Yeah, like you can actually think about this equation as if you act with phi on S, the columns of this matrix are essentially giving you a dual basis to the effects E. And so because phi, the action of it has the form of an Ergleichung, indeed the dual basis is related to the POVM elements in just the same way. Yeah, so that you're right.
Thank you.
Mm-hmm.
Okay. Are there any further questions? If not, then let's thank again Matt for the talk.